specific heat, exo versus endo, and system and surroundings. So just a reminder, there was a whole lot of equation stuff. They used S instead of C for your heat capacity. And everybody tested different salts. So just a reminder, we had these different equations, Q solution, Q of the water, Q from the calorimeter. We had an average temperature. We found the heat capacity of the calorimeter that was included. Okay, so this is a lab we did. So I did not have you answer the integrated question of how these things all relate. And so I actually am going to jump to the other keys for that. Okay, so this is the integrated part, I think. Yes. So the integrated part I think what makes this one harder is just, I think thermal is harder. So here's the questions by themselves. This takes to. So review the following data from the calorimetry experiment to determine the heat of fusion of ice. After shaking off any excess water, several ice cubes were added to 99 grams of water containing a calorimeter. The initial temperature of the warm water was 46.8 degrees C. The ice water mixture was stirred until the temperature reached a stable minimum value, which was 1.1 degrees C. Any unmelted ice remaining at this point was immediately and carefully removed using tongs, and the mass of the water in the calorimeter was measured, 154 grams. So you'll see it's kind of the opposite of what you did in this lab. So you're also finding the heat energy equation, calculate the amount of heat in joules released by the warm water as it was cooled. You're looking at the conservation of energy, turning the amount of energy absorbed per gram of ice melted, finding the heat of fusion, percent air, that goes on. So, question like this, you have done a lab similar to it, but doing the opposite with making things colder instead of warmer and working with ice kind of freaks people out sometimes. So let's look at how you do this. So use the heat energy equation to calculate the amount of heat in joules released by the warm water as cooled. So here's the delta T. So you just find the two different temperatures. So the Q of the warm water, you're taking your mass of that 99 grams, the capacity of water, delta T, gives you the negative 18,900 joules. Then based on the law of conservation of energy, which amount of heat was absorbed by the ice as it's melted. This is an example you overthink it, that if they're opposites, so whatever's given off by one was going into the other. And so here they're just making it a positive 18,900. Determine the amount of energy absorbed per gram of ice as it's melted. Okay. Do show subtractions with something as simple as this. Do show the subtractions. Amount of energy absorbed per gram of ice as it's melted. You're going to take the heat of the ice over the mass of the ice. So that's 340 joules per gram. And then calculate the heat of fusion, the heat required to melt the ice, in units of kilojoules per mole. So now we're just playing with units, really. We take the joules per gram, and we're going to convert those grams to moles using our molecular weight, and then we're going to convert it to kilojoules. So then they gave you the value of 6.02, which is the one you know. Use the percent air formula, something like that you might have to pull out, who knows. And then when a mixture of ice and water originally at 0 degrees C is heated, temperature remains constant within a few degrees. Explain what happens. So the energy absorbed disrupts some of the attractive forces that holds the water molecules in the rigid structure of ice. There's really not much you just can say about this one. Or can I think they come up with